Hi everyone, welcome to this video for Computer Science 110. This video is going to cover search. Alright, so how does one find an element in a list? So let's just say you had an element that you wanted to find in a list. How would you go about actually checking if some element is in a list? Well, one way that's built into Python is you can use the in keyword. The in keyword can tell you if some element is in a list. Now, what if I told you, or what if I asked you to find an element or check if an element is in a list or not? Not necessarily to find the index that it's at, but just to tell me, is this element in some list, but without using the in keyword and without using if there's any other built-in methods to lists that would allow you to find it easily without using any of those kinds of functions. So how would you go about doing that in a way where you actually loop through the list to check if the element is in there or not? Well, one thing that you can use to check if an element is in a list is what's called a searching algorithm. So essentially, what you can do in Python is you can actually write a function where you give that function a list and where you give it some element in a list or some element to check if it is in the list. It might not be in there, and have that function return true or false. And what you can do if you're not allowed to use the in keyword is you can write an algorithm to go through and search through that list to see if the element is in there. So maybe I should say, I'm just going to get rid of this one here. We're going to focus on two different kinds of searching algorithms. So one is a pretty simplistic one, sequential search. And the idea here is you basically just loop through your whole list and check if you find an element or not. So let's say you were asked to find 15 in the list 1, 2, 5, 15, 3. So the way that the algorithm would work is it would check the element at index 0. If it doesn't find it, then check the element at index 1, check the element at index 2, check the element at index 3. Once it finds it, it can return true. Now, if you were instead of 15, where you were asked to search for 25, it could go through everything, all of the values in the list, and if it doesn't see it there, then it could just return false. So that's the basic idea, pretty simple. So how would you go about writing the code for that? Let me change this parameter to E for an element. I'm going to change that throughout the slide here. All right, so the way to do this, again, I'm going to change this to E here for element. So what you could do is write a loop that iterates through, in this case, you don't have to do it through the indexes. You can use a for loop, which can go through the values directly. You could also do this with going through indexes using the range function or something like that. And if you find the element, go ahead and return true. And then if you made it through the entire for loop here, but if you never got to the point where you return true, then you should be able to safely say that E does not exist in the list L, so you can return false. All right. So what would this operation look like visually? Well, if this was items and this was a sequential search, right, you would only need to look at one element and you would find that 5 is in there. Great. What about here? So if for this one, how many times would you have to look at a value in the list to determine if 7 was in the list or not? Well, you would have to do 1, 2, 3, 4, 5 checks, because on the 5th check you would see that 7 is in there and then true could be returned. So that would take 5 checks. What about for 43? Well, for 43 it would take 1, 2, 3, 4, 5, 6, 7 checks, and 43 is the last element in that list, so at that point you could return true. Now, what if you were searching for something like 100? Well, if you search for 100 using sequential search, you'd search through all of the elements and you would not see 100 in there for this particular case, and then false would be returned. So one of the downsides of the sequential search algorithm is that if you're using the simple sequential search, and if you're searching for a value that's not in the list, you will end up going through and checking every value in your list before you can safely say that that is not in there, if it is an element like 100 that's not in that list. So this can be pretty bad, because if you think about this list, in this case it might not seem like all that much because this list only has 7 elements in it. But imagine if you had a list with 10,000 numbers in it. And what if the user wanted to do a search for a number that was not in the list? Well, in order to see that it's not in there, you'd actually have to go through, if you're using sequential search, in order for Python to know that, it would have to go through and check all 10,000 elements, which could be very inefficient using simple sequential search. So let's think about this. So on average, this is a kind of a question I want you to think about. So say that there's some list named L, right? If you're doing a sequential search for element A, and let's say L has some number of elements, and the n can be what we think of as the length of the list, and the elements, don't assume that there's any kind of ordering, assume it's just totally random numbers. How many, on average, checks would you have to do in terms of L? So what I want you to think about it is for several cases. So let's say you have a list L of length n, and you want to search for A, but let's say in advance we know that A always exists in L. It's never going to not exist, we just don't know where it's going to exist. It could exist at the beginning or at the end or in the middle. So on average, how many checks would have to be made in terms of n? All right, well, I'll bring up the answer and then I can explain it to you. So the answer is basically n divided by 2, or that's actually close to the answer. It might end up being more like n plus 1 divided by 2. So why is that the case? Well, if you think about this, right, if n is 5, so if there's a list of length 5 with 15, 10, 7, 4, and 22 in it, 5 elements. So, and if you're doing searches for things that always exist, so let's say the user searches for 7, well that's 1, 2, 3 checks. If they search for 22, 1, 2, 3, 4, 5 checks. If they search for 15, that's 1 check. So if you actually come up with and do the averages for this, what it would end up being, I think, is actually something like n divided by 2 plus 1. Maybe not n plus 1 divided by 2, n divided by 2 plus 1. But basically it's about, on average, you'd have to check 50% of the elements, or maybe 50% plus 1. So we can ignore, for the purposes of this slide, we'll just ignore the plus 1 in the solutions. Just to keep it simpler, we'll say n divided by 2, and because when I first wrote these slides, I may not have been considering the plus 1, but we'll just say n divided by 2, right? So that's not so bad for a small list, but if you have a list of 10,000 elements, and if you're going to do a lot of searches in your program, on average, even if A always exists in the list, on average that's 5,000 searches. That could, if you're doing a lot of searches, be costly. Though even 5,000 elements, a computer can scan through pretty quick. But if you're doing that scan a lot of times, that could get expensive. So you can also think about it as n times 1/2. All right, so if A only exists in L 50% of the time, how does it change? Well, for 50% of the time, here's kind of a way to think about the math. So for 50% of the time, we can assume that it's n divided by 2, which really it might be n divided by 2 plus 1, but let's not worry about that, times 0.5. And then for the other 50% of the time where the element does not exist in the list, in that case, you'd have to scan through all of the elements, every one of the elements in the list. So that would just be n times 0.5. So what does this come out to if you reduce it or simplify it a little bit? It comes out to n times 3/4, which is more than n times 1/2. And then if you move on to say, what if A exists in L only 25% of the time? you can do this, but you multiply the n divided by 2, again, ignoring the plus 1, times 0.25 and n times 0.75, which can become that. So anyway, if you have a really big list, and if you're doing lots of search, like big list is in 1 million or 5 million or 10 million elements in it, and if you're doing a lot of searches, and if some of the time, maybe a significant amount of the time, the element you're searching for doesn't even exist, sequential search might not be a good choice if you're going to do a lot of searches. So can we do better than sequential search? The answer is yes, but with a caveat. Okay, so come up with a better algorithm for searching. So perhaps you could take a minute to try to think of an algorithm that would be better for searching than just sequential search. So can you think up something that would be better? What kind of adjustment could you make? Would it be a tweak to sequential search, or would it be a whole different algorithm? What could do better than sequential? All right, well, something that can do better with a caveat is binary search. So binary search can be much more efficient, but it assumes, or in order for it to work properly, it has to assume that the list that it's searching through is already sorted, which sorting can actually be expensive if it's a lot of data. But if you're allowed to assume that, and if it is truly sorted, binary search can be, in many cases, much faster than sequential search. All right. So if your data is sorted, it can be faster. Wait. Yeah, okay. So let's look at this example here. So let's say that these are some people that are lined up and sorted by when their birthday is. So for the purposes of this example, let's just say that this guy has his birthday on 1/19, so January 19th, whereas this guy has his birthday on 11/7, so November 7th, right? So if you can assume that these people are sorted, how does binary search work? Well, basically, let's say you, even though these are shown here, let's pretend that you didn't actually know exactly exactly what the birthdays were, or even which birthdays they were. So let's pretend, oops, oh, what's that doing? Oh no, did it stop the recording? Shoot. Wait, oh no, sorry. It's a dust area project. Okay. All right, so let's pretend that you don't know what everyone's birthday is. You just know that they are in sorted order. So let's say you wanted to check and see if 4/5, or let's do 4/7, is in some. Let's see if you want to check if someone has that birthday. So the way that binary search would work is you would basically find the middle point, which in this case, since there's an even number of people, there's no exact one person in the middle. So what you would do by default is, if you have something like this where there's not one middle person exactly, is go to the one right before the middle person. And then you would ask that person, what is your birthday? And if she said 5/15, you would know, okay, 4/7 is earlier in the year than 5/15. Since you can assume that everyone's in sorted order in this example, you can then ignore all the rest of the people over on that side, and you can actually ignore that girl too, because you asked her what her birthday was and it was bigger than 4/7. So by doing one check, you've already eliminated over half of the people in this case. So then what you do is, with your remaining people, you basically follow this same step, but only on those remaining people. So find the midway point. If there's no exact halfway person or person in the middle, go to the one before, and then ask, in this case, that woman what her birthday is. So if she says 1/25, then you know that 4/7, if it's in here, which it's really not, but if it is in here, it would be that direction. So you would get rid of them. And then you would take these two guys into consideration, middle Ask him, 317. Also too low. So now on the fourth check, you're down to one person. So you can ask him, what is your birthday? If he says 4-4, that's not the birthday you're looking for. And all right, so no one has that birthday. So now let's do another example where we actually end up finding it. We'll do 815. Let's see, do we want to do 815? Yeah, we'll do 815. All right. So another way to think about this, though, when you're actually doing binary search is you can think about it as you kind of have these two marker points, right? So you have a beginning and end marker point, and as you ask questions and sort of figure out that you can ignore parts of the list, you can slide these, depending on what question you ask, one or the other, more and more in. All right, or at least more and more to the other side. So find the middle. Ask her what her birthday is. 515. Okay, well 815 is more than 515. So instead of thinking about it as just scratching over those people, think about it as we can now move that bar up to here. So now we only have to consider the people in that range, whereas before we were considering every one of them. All right, so now in this case we can look for the middle, and there actually is a guy right in the middle. So ask that guy what his birthday is, 9/14. All right, well that's greater than the birthday that we're looking for. So we will slide this bar. We can actually slide it past him since his birthday was greater. All right, so now we only have to consider those two people. So we find the middle, ask him. 810 is earlier in the year than 815, so we slide the bar that way. And now we're down to just one woman, and we can ask her birthday and figure out that, yes, there is someone with 815, that girl. All right, so basically in both of those scenarios we had to do, let's see, 1, 2, 3, 4 questions asked, but we were even able to figure out that the birthday 47 did not exist in among all the people with only 4 checks. Whereas with sequential search, sometimes, if we were searching for 119, yeah, we might happen to get it on the first check. But if we were looking to see if someone had the birthday 11/7, there would be a whole bunch of checks to do before getting there. Or if we were looking for a birthday that didn't exist, you'd end up checking all of them and then having to say it's not there. So the worst case scenario with binary search is better because you don't have to always, if your list is large enough, you do not have to check every element to see if something is not in there. Okay, so given this list, how many checks would it take to find 55? Well, so to find 55, let's see, is it in there? Yeah, it's in there. So what would we do? We would find the middle point, and let me do this here. All right, so the middle point, let's see, there's 14 total elements. So the middle would be right here, but since there's an even number of elements, there's not an exact middle element, so we would go and ask there. And we can think about our 2 kind of bars on either side. And since 12 is less than 55, we could take this bar and move it up to right there. All right, so now find the middle in here. There is an exact middle, which is right there. And that happens to be, or the value there, not the index there, happens to be 55. So we can check if that's greater than or less than or equal to 55. It's equal. Boom. We can go ahead and return true with after that point. So 2 checks. All right, how many to find 4? How many to find 20? Okay, so the algorithm, what does the algorithm look like? Well, the code itself is a little bit more complicated, and I'm actually going to change this to E also. E, yeah, okay. So here's a version of it where, as a part of the function, a call to this sorted function is called, which gets the list in sorted order, or it probably, let's see, I don't know if it changes the list or returns a copy, but it does some sorting, and then basically this is the algorithm itself. But if you can already assume, if you're allowed to assume, that the list is already sorted, you don't have to have that line in there. Now, how is this working? Well, you can think of these two numbers kind of like the bars on either end of the visual lists, where those are going to be numbers that are referencing an index, which is the beginning inclusive and end inclusive of the range of possible locations that the element you're searching for could be at. I'm going to change this to E, E, and E. So you can think of first and last as those markers, and then this loop is for repetitively kind of doing those checks that we were doing until either we find it. Well, in the loop we would return true if we found it, or if the loop finishes and does not return true, then you could return false. So this here is for basically calculating the middle point between first and last. And let's see, given the way that this one works, yeah, so this is for calculating the middle point. But I'm trying to think if this would end up getting the one before or the one after, if there's a tie. So it might be getting the one before, it might be getting the one after, but it should work either way, even if it isn't doing it identically to what we talked about earlier, but it might be. And so then, technically, even though we were talking about one check before, or I was talking about that, technically the way that this is written, for one iteration of the loop, there could be multiple checks because there's an if, elif, else. So it could check if it's equal, and it could end up checking if it's less than. So technically, when you're visiting one number, it could be that it actually evaluates two conditions. So, you know, one of those checks could actually end up being two conditions evaluated. But anyway, if it's equal, you can return true. If the element you're currently at, if it's less than the value that you're looking for, then you can take your first index marker and move it up to check +1. And then in the else case, you can change last to be check -1. And then basically this can keep looping, and then until if first ever becomes greater than last, then your markers, so as you're doing, let's see, where's my other hint here? As you're doing your search, if this moves up and this moves up and this, if they ever cross paths, then that means you would have basically ruled out everything in the sorted list from being what you were searching for, and then you can go ahead and return false. So what would be the number of steps to find 5 given that list? Well, in this case it would be, let's see, 1, you do that, and then the middle there, and then there, so 3. How about for 11? Well, for 11, it would 11 is not a value in that list. It's not a value in the list, but it would only take 1, 2, 3 checks to determine that it is not in there. But 11 is not in that list, so 3 is all it takes to determine that it's not in there. Okay, so there's a few other number of steps things here. So if you actually do the math out, kind of very roughly, so in big O notation, when you're doing sequential search, or excuse me, sorry, when you're doing sequential search, the worst case is not very good. The worst case is actually that you could visit n elements. Now, you don't have to just consider the worst case scenario, but in binary search, even the worst case scenario is somewhere right around log n, where n is the number of elements in your list. So it could be less than that. You could only have to look at 1 or 2 elements to check whether something's in your list. But even the worst case, where you have to, if you're searching for something that's not actually in the list, log n is basically about as bad as it gets. Let's see, is it log n or is it? It's somewhere close to log n, yeah. So So the positive thing about binary search is even the worst cases generally are not that bad. So let's see, searching algorithms. Yeah, okay, so one other thing I want to show you, and I have to actually go, let me go to class website from spring 2019 and download this. Oops, oh, okay, interesting. Well, let's see. I think I can, give me a minute here. So let me, all right, so I copied over a program called, what did I call it? Search timing. So let me see if I can open this up here. All right, so what's going on with this code? Well, there is a binary search function, which again, I want to change this to E. Really, these actually should be more descriptive variable names, but I could call this list to search in an element or something. List to search in might be a little verbose. But anyway, a function that can do the binary search and a function that can do a sequential search. And then a few other things here. So here is a function that can get a random list, although wait, let's see. That's not actually getting a random list, that's getting a sorted list. Sorted, because of the way that it is, it's basically doing a loop through range and appending I. So it's getting a sorted list actually of, let's see, probably integers, yeah. And then what happens, or what other functions are there? So this other function here, time list test, which is, part of it happens before get sorted list, but then get sorted list gets called from that function. But time list test is going to do a test for those two searches. So basically what it's going to do is, given this list L, it's going to do a bunch of searches for random numbers that are in some cases in the list, in some cases not, via sequential search. And it actually uses the time module to time how long that takes, and then it reports that via print statements. And then it also does a bunch of searches using binary search and then reports how long that takes. And so right here from main, timeless test can be called, and basically this number determines how big that list is or how many elements are in the list that it will do the test with. So if I run this based on a list of 10,000 elements, both of them go pretty quick. So sequential search took 0.018 seconds to do 100 searches through a list of that big. And binary search, it probably took some time, but it went so fast that it reports it as 0.0. All right, so what if I go from 10,000 to 100,000? Oops. So 10,000 to 100,000, still pretty quick for sequential search, but 0.195 seconds and 0.001 seconds for binary search. So let's up this a little bit. Let's go all the way to 10 million elements. Let's see. So it's running. All right, so there we go. So for sequential search, 17.084 seconds. For binary search, 0.001 seconds. So binary search was way, 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 way faster for a list of 10 million elements. So now the caveat with binary search is you have to, in order for it to work effectively, the data that it's doing a search through has to be sorted. And sorting a lot of numbers, a big data set, can be expensive if it's really unsorted. But if you have something that's sorted, then binary search can be really good. Okay, that'll wrap up this video.